Welcome back to Math Defined. I'm Mrs. C, and today we're going to explore finding the probability of compound events and how to use tree diagrams to organize the specific outcomes for those events. Imagine you're designing your team's soccer uniform. You get to pick a shirt, a pair of shorts, and socks. That's just 3 choices, right? But here's the twist. Those 3 choices can combine to make way more outfit possibilities than you might expect. And that's exactly what we're exploring today. When you make more than one decision, like picking a shirt, shorts, and socks, it's called a compound event. Each part of the uniform is one event, and when they all happen together, they form a compound event. Let's take a look at your team's uniform options. For the shirts, you can choose red, yellow, or green. For the shorts, you can choose black or white. And for the socks, you can choose striped or solid. How many different uniform combinations can you make using one shirt, one pair of shorts, and one pair of socks? The complete list of all these combinations is called the sample space. And to help us keep track of everything, we'll build a tree diagram. But before we jump into building our tree diagram, let's take a moment to understand what it is. A tree diagram is a simple way to organize and show all the possible outcomes when you're making more than one choice. Each branch in the diagram represents a decision, like choosing a shirt and a pair of shorts. As you move from left to right, each branch adds on to the choice before it. Instead of trying to list all the possibilities in your head, a tree diagram lays them out visually so you don't miss any combinations. It's especially helpful when you have lots of choices and want to make sure you've covered every possible outcome. Now, let's build one. We'll start with the shirts. Since we have 3 choices, red, yellow, and green, we'll draw 3 branches, one for each color. From each shirt option, we'll add 2 more branches for the shorts, black or white. Then for each shirt and shorts combinations, we'll add 2 more branches for the socks, striped or solid. Now that the tree diagram is complete, we can follow the branches to list all the uniform combinations in a sample space. Let's start with the first full path, a red shirt, black shorts, and striped socks. We'll write this in the sample space as red shirt, black shorts, and striped socks. Now let's follow the next path. It still starts with a red shirt and black shorts, but this time the socks are solid. That gives us a red shirt with black shorts and solid socks. Can you find the next 2 combinations? I'll give you a hint. We're still on the red shirt branch. Red shirt, white shorts with striped socks, and then a red shirt, white shorts with solid socks. Great! Now we've found all the combinations that start with a red shirt. Let's do the same for the yellow shirt. Yellow shirt, black shorts, and striped socks. Yellow shirt, black shorts with solid socks. Yellow shirt, white shorts, and striped socks. And a yellow shirt, white shorts with solid socks. You're doing awesome so far. Now let's finish up with the green shirt combinations. Green shirt, black shorts, striped socks. Green shirt, black shorts, solid socks. Green shirt, white shorts, striped socks. And green shirt, white shorts, solid socks. And that's it. All the paths have been followed, and every uniform combination is listed. So how many total uniform combinations do we have? Let's count them. There are 12 combinations in all. That's our complete sample space. Tree diagrams are super helpful for listing all the specific possible combinations you could make. But what if you just wanted to know the total number of combinations? Would you still need to draw a tree diagram? Luckily, there's a shortcut for this called the fundamental counting principle. It's a quick and easy way to find just the total number of outcomes without drawing a tree diagram and completing a sample space. All you have to do is multiply your choices together to get the total number of possible outcomes. Let's try it with our uniform choices. We have 3 shirt color options, 2 shorts options, and 2 sock choices. Now we just multiply them together. 3 times 2 times 2 is 12. That's the total number of uniform combinations that can be made. Pretty easy, but remember, this just gives us the total number of combinations, not a list of all the specific ones. What if you really wanted one specific uniform combination, like your absolute favorite, a yellow shirt, white shorts, and striped socks? What are the chances or the probability of you actually getting it? We're going to need to use our sample space to figure it out. To find the probability of getting that exact uniform combination, we need to ask, how many outcomes are there in total? We already know there are 12 combinations in the sample space. Now, how many of those 12 include your favorable outcome, a yellow shirt, white shorts, and striped socks? Just 1. So we have 1 favorable outcome out of 12 total possible outcomes. That means the probability is 1 out of 12, or 1/12. If uniforms were handed out randomly, you'd have a 1 in 12 chance, or about an 8.3% likelihood of getting that specific uniform combination. Who knew that using just a little math along with our sample space, we could predict how likely something is to happen? But what if you only cared about getting black shorts? What would the probability be for that? Let's look at your sample space again. How many combinations include black shorts? 1, 2, 3, 4, 5, 6. I see 6 combinations. So the probability of getting black shorts is 6 out of 12, or 50%. Today you've learned how to build a tree diagram to find all the possible outcomes of a compound event and then list them in a sample space. You also learned how to use a shortcut, the fundamental counting principle, to find the total possible number of outcomes without building a tree diagram, and even figured out the probability or the likelihood of a specific event happening. You did an awesome job today. If you found this video helpful, give it a thumbs up, hit subscribe, and hey, if you made it all the way to the end, drop a sock emoji in the comments so I know that you're part of our Math-Defying crew. Thanks for watching, and until next time, keep math awesome.